it is my great pleasure to introduce our next speaker. As I was saying early on, I'm very, very pleased that the new organizers of WIL kind of gave me this chance to talk to two exceptional computer scientists that are also extremely nice people. And the second one of them is Alexandra Silva from the University College London. And Alexandra has lots of things that one could say about her and stuff. I'm not going to, if I started doing that, I will have to go on forever and ever. So I think I'll just let her talk about algebraic. I mean, that's one of the things that I discovered recently, Alexandra, is that you're a professor of algebra, semantic and computation. I was so jealous. I want to be one too, you know.
This is a very UK thing. You can choose your own title. So that's kind of nice.
Anyway. Sure. That's so cool. You chose to be a professor of algebra. Excellent. Good taste on top of everything else. So take it away.
Yeah, thanks, Valeria, and thanks everyone. It's a great pleasure to be here today. It's a real shame we cannot be in the same room, but I have to say, I joined in halfway through Maribel's talk. I'm currently in Wisconsin on sabbatical, so it is a bit early here, even though for Valeria is even earlier, so I have no excuse really. And I was noticing the atmosphere among the participants in the gallery, and it's a real, it's a real change from other workshops I've spoken at. So it's a great pleasure to be a speaker at Women in Logic. I think this is the 4th edition, and it's a great initiative. So thanks for the invite, and I hope I can share a little bit about my research, and at the very end, I will say, I will spend few minutes talking a little bit about what I think is being a woman in logic, at least from my personal perspective. So today I would like to tell you a little bit about a project that really has been the PhD project of one of my students who is actually defending next week. So this is sort of a 4-year project, and it was something when he started we thought we could do in a few months, and as with many research questions, you soon find out that things are much harder than you think at the beginning. So let me start by giving you a little bit of context, which is also related a little bit with my career path. And back when I was a grad student and later when I was a postdoc, I did a lot of work on Kleene Algebra. And Kleene Algebra was introduced by Dexter Cozen back in the early 90s, late 80s, as an algebraic foundation for program verification. And the theory of Kleene Algebra is well developed, and there are results on completeness of the system and also on procedures for equivalence and so on. And it has a lot of applications, and Dexter and his students and other people who have followed on his lead have looked at using Kleene Algebra to reason about compiler optimizations and program schematology and much more. In the last 5-6 years, there's been a lot of focus on extensions of Kleene Algebra with additional structure to reason about control structures in programs. And so Dexter himself had already introduced in the 90s a system called CKAT, Kleene Algebra with tests, and that has been more recently extended to include other operators. So in particular, one system that is of interest to me is a system that was introduced by Nate Foster and collaborators called NetCat. And in the last 5 years, I've dedicated a lot of my research into a probabilistic extension of NetCat and tools related to that. So why Kleene Algebra, and why is Kleene Algebra a good foundation for a verification framework? So one thing is Kleene Algebra comes with a compositional semantics, meaning that more complex programs can be, you can reason about complex programs by reason about its smaller pieces. And this is very amenable for scalable verification. And there's this fundamental correspondence in Kleene Algebra between automata and language theory, or say the semantics of the of the language. And that correspondence can be explored in a in various ways to do verification. And this is sort of the reasons why Kleene Algebra has been so successful as core framework for verification. So the thing we have been looking at in the last few years is to sort of extend CKAT in this layered way that in order to increase its expressivity, but at the same time without losing the properties of the core language. So CKAT, as introduced by Dexter, was only enough to reason about simple imperative programs. So programs that have conditionals like if then else or while loops. Then back in 2014, an extension called netcat appeared, and that extension basically added two constructs that enable to talk about local state in a packet traveling a network, and those constructs were then enough to reason about reachability. Then we looked at extending netcat with a probabilistic construct, and that enabled us to reason about congestion. And sort of the principle in all these extensions is that you want the extensions to be conservative so that you can inherit semantics and algorithms from the lower layers. And you want to basically be able to retain all the results you have. And now what I want to do in this talk is to show you that the last layer, to reason about concurrency, requires a little change in the sort of core layer. So the core layer, CKAT, didn't have any construct to talk about concurrency. So if we have any hope of adding a layer in which concurrency can be reasoned about, then we need to actually take a step back and look at the core layer. And so that's what I'm going to do for the coming 20 minutes. So in this talk, basically what we want to show is that as in the 90s, Dexter went from Kleene Algebra to Kleene Algebra with tests to add constructs to reason about control flow. And in sort of orthogonally, Tony Hoare and Georg Struth and many others have looked at extended Kleene Algebra with a concurrent operator leading to CKA. We would like to now somehow marry these two frameworks and combine them into one. Now, I should say that this combination was studied by extensively by Peter Gibson and by Peter Gibson and Drew Moshe back in 2014 and 2016, and briefly also touched upon a paper of Peter O'Hearn and Tony Hoare. And when some years ago, back in 2015, Valeria and I were actually at Wallach in Indiana right around this time, and I met Peter Gibson there. And I told him this plan I had for the fall when I was starting in London, of starting to look at CKAT basically. And he told me, oh, here's a paper. And actually I've done it. So I took that paper with me and I thought, okay, he's done it. That's great. And when my students started, I was like, oh, look, Peter Gibson has actually done this. So we can just build on it and it's easy. And it turns out it was not so easy. And in fact, Peter Gibson's framework had a property that was not desirable for verification. And I will show you that later. And this is sort of when algebra and verification collide in an interesting way. This is one of the things I would like to show you later. But let's start from the beginning, just to sort of set some notation and see. So Kleene Algebra is the algebra of regular expressions, and this goes all the way back to Stephen Kleene in the 50s. And here are some examples of regular expressions. I think most of you have seen this, but the idea behind regular expressions is that they give you a really simple syntactic way of capturing patterns that repeat in a certain language. And Kleene's original paper had this result, which has become one of the cornerstones in theoretical computer science, that basically showed that the languages denoted by regular expressions are exactly the languages accepted by finite automata. Now, you can look at regular expressions as denoting the traces of a program. And so you could interpret the letters in the alphabet as being atomic actions, and then you could interpret the 0 and the 1 as the usual abort and skip. And the plus can be interpreted as non-deterministic choice, and the C dot or the semicolon can be interpreted as sequential composition, and the star is just repetition. So Kleene Algebra is the algebra of these expressions, and it's basically a set of axioms that enables you to reason about equivalence. And so regular expressions, or Kleene Algebra, is a structure that has the following properties. So first of all, it is a joint semilattice. So you have a 0. So the 0 is the neutral element of the plus, and the plus is either potent and commutative and associative. It also has the 0 is also the absorbent element of sequential composition, and the 1 is the neutral element. And then the times and the plus distribute in a reasonable way. And the star basically is axiomatized as a least fixed point of unfolding. And these, in the 90s, so Dexter showed that these axioms, these 11 axioms, are enough to reason about equivalence of regular expressions. And so you can do equivalence can be done via completeness, so using the axioms, or you can use Kleene's theorem and translate the expressions into automata and then reason there. And for automata, there's all kinds of efficient algorithms. Again, this goes back to the 80s with Hopcroft and Karp, and then more recent improvements like anti-chains and bisimulations up to. So there's all kinds of algorithms to look at equivalence of automata. So you can kind of reason about regular expressions in different ways. And there's also, what is interesting is that there are algorithms that combine some of the automata ideas with the axioms, and bisimulations up to is one of those that you can use. So you can use what you know from the axioms to kind of speed up your equivalence reasoning. And why is equivalence something I keep bringing up? Because as it turns out, equivalence is essential to many verification questions, and you can reduce a lot of verification questions to equivalence questions. So in particular, in this NetCat framework from 2014, all the things related to reachability were reduced to equivalence questions, and then they were checked using the axioms. And then later on, we have a paper in 2015 where we show that bisimulation can be used to do it more efficiently. And when it comes to regular expressions, they still keep somehow giving us research questions, and efficient fragments are still being studied. So still this year, in January, we had a paper basically showing that you can restrict the class of regular expressions to get a more efficient framework where you then can do equivalence even more efficiently. So that's for Kleene Algebra. And then once you have Kleene Algebra, you can start extending it. And so the first extension that Dexter looked at was this Kleene Algebra with tests. So the idea behind Kleene Algebra with tests is simple. You take a Kleene Algebra and you split your alphabet into two. You reserve one part of the alphabet to still talk about your program actions, and then you take the other part and you say, okay, these other letters I'm gonna use as tests. And from that other part, you generate a free Boolean algebra. So you want them to be tests, so you want to be able to combine them using the usual structure of a Boolean algebra. So what you end up with is basically a two-sorted structure in which you have a Kleene algebra and you have a Boolean algebra that is embedded into this Kleene algebra, because you basically have reserved some of your alphabet to talk about tests. And so if you have that, you can then encode simple imperative programs as regular expressions. So for instance, the conditional if B then P else Q can be encoded as B followed by P and not B followed by Q. And the same thing for the while. So the while loop can be encoded as BP star. So you iterate on P on the body of the loop while B is true. And then at some point you exit the loop because not B is true. And the semantics of CKAT is quite similar to the one of regular expressions. So you still have regular subsets of words, but now the words are a bit more complicated. So instead of just having the letters of the alphabet, you also have, so intertwined with the letters, you have the atoms of your Boolean algebra that basically tell you what is the state of your program variables. So let me give you an example. This is easier through an example. So for if B then P else Q, then your semantics now is a language that has two words. One word says at the beginning, I have an atom that asserts that the test B is true, and therefore I see P in the next step. And I end up with some state beta that I don't know what it is. After P, anything can happen. And then the other option is that I start at the start of my execution, not B is true, and then that should be a Q there in the second letter. And then I have a Q, and then I end up with a beta. And for the while loop, you have a similar unfolding. So you either have not B is true, and therefore you never see the body of the loop, you never see P, or you have B is true once and you see P, and then not B is true, or you have B is true twice, and then you see P twice, and etc. So you have this increasing length of traces where you see P n times, and if you see P n times, then the test B must have been true n times. Otherwise, the semantics would not be capturing how the loop is supposed to unfold. Okay, so so this is CKAT. So it's a simple extension of Kleene Algebra. And what is nice about CKAT is that because it's a conservative extension of Kleene Algebra, you can actually, in a sort of principled way, show that if you take the Kleene Algebra axioms and you add the extra Boolean algebra axioms that you need for the tests, then these are actually sound and complete. And you can do completeness again using the axioms, or you can do completeness via an extension of Kleene Theorem that uses a special version of deterministic automata called guarded automata. And CKAT has this interesting connection with Hoare logic, for those of you who are familiar with Hoare logic. So the validity of a Hoare triple that has the propositional Hoare triple that has precondition B and postcondition C can be reduced to an equivalence question. In particular, it can be reduced to the question that I have B, I then have P, and if at the end I see not C, then this is equivalent to 0, meaning I must see C. Otherwise, this equivalence is not right. And so there are different ways of capturing validity of Hoare triples as equivalence questions. Now, so at this stage, we basically have, I think there's a question from Maria Paula, I think.
Yes, thank you.
Okay.
Could you please remind us what you mean by conservative? Because conservative has different meanings in logic. And
Okay, okay, that's a good point.
The one you're using. Thank you very much.
Thanks for the question. So what I mean is something very basic. I just mean that if you restrict your terms to the terms that that are pure Kleene algebra terms, then the semantics actually gives you the same semantics as before. Because basically what you will have, if you take an expression without tests, you will have a semantics that has tops everywhere. So in terms of the atoms, you just get tops everywhere. And if you delete the tops, you get exactly the regular language that you started with. So that's what I mean. Okay, so so we have Kleene Algebra, which allows us to reason about certain patterns, and then we have Kleene Algebra with tests that adds basically the capability to reason about control flow. And now we would like to basically reason also about concurrent programs. So we would like to reason about threads in parallel. So let me give you an example, and maybe we can then talk about what is needed in order to reason about such programs. So this example here, I copied from Peter Sewell's webpage. So there's a whole webpage on something called litmus tests, which are small concurrent programs that are notably hard to reason about. And so here's one program that has two threads, T0 and T1. And those threads have basically two instructions. And they are manipulating two variables, X and Y. And those variables start at 0. And so thread 0 will change X to 1. And then it will copy the value of Y to some register R1. And then thread 2 is basically changing Y to 1. And then it is copying the value of X into R2. And one thing you might wonder at the end is whether at the very end of this execution, I can have R1 different from 0 and R2 different from 0. So if you stare at the program for a moment, you will see that because these threads are in parallel, what can happen is that, for instance, thread 0 executes fully before thread 1 starts. And if that is the case, then R1 will have value 0 because Y wouldn't have changed. But if R1 has value 0, then X must have changed because X happened before R1 changed. That means that whenever thread 2 does anything, the value that gets copied to R2 must be 1. And you can do the reverse reasoning. So if T1 executes fully before T0, then, then Y must have changed to 1. And maybe R2 is 0, but eventually R1 in the other thread must be 1. So this is sort of a hand-wavy reasoning, and honestly, I'm not even sure I could convince you fully that this reasoning is sound. But you see where the subtlety comes from. I mean, we have these two threads that have these sequential operations, and we don't know when each of them executes. And they are somehow communicating via this common register store, and therefore this will influence the end state of that store. So we would like to be able to reason about these programs in the same way we did about simple imperative programs. So we would very much like to be able to prove that, that this program indeed satisfies some reasonable assertions at the end. And there was some first proposal by Tony Hoare and Georg Struth and collaborators that indeed you could extend Kleene algebra with the parallel operator to represent threads executing in parallel, and that then you can reason about traces. Now, that work didn't have control flow, but you could already use it to specify at least parallel threads. So ideally, I would like to be able to show that the program above is correct by proving the following equivalence: that if I start with X is 0 and Y is 0, and then I execute T0 and T1 in parallel, then at the end, so this should imply that at the end, I cannot have both R1 and R2 being 0. So one of them must have changed to 1. So the thing about concurrency, and I like this cartoon, is that you know, I hand waved in the previous slide, and I kind of tried to hand wave my way that that program does what's supposed to do. And I might even convince you, but if I want to automate this reasoning, if I want to be able to say this about more complex programs, I mean, it took a few minutes to explain a 2-thread, 2-line program. So now imagine if I want to talk about programs that have, you know, let's say even hundreds of lines, not even thousands, but let's just say, you know, a few dozen lines and a few dozen threads, this reasoning becomes more complex. And there's been a lot of attempts of developing frameworks, and there's a lot of things out there that work really well in very specific domains. And what I would like to do is to try to understand sort of the algebraic properties that are at play there. So as I mentioned a couple of times, Hoare and Struth and Moeller and Wehrmann introduced this idea of concurrent Kleene algebra back in 2009, which basically is Kleene algebra with an additional operator, parallel, and the semantics of this new language was proposed by them as languages of POM sets, partially ordered multisets. And so the idea behind partially ordered multisets is that they are simple generalizations of words in which you can really keep track of the order of events, and at the same time also keep track when things happen in parallel. So for instance, the little program there, A followed by B parallel C followed by D, would be represented by a language that has one POM set, namely the POM set depicted there that has action A and then has this branching into B and C in parallel, and then D at the end. And you would expect that this being an extension of Kleene algebra, they would have looked at a Kleene theorem and axiomatization and decision procedure. But as it turns out, just understanding the language, just coming up with the semantics and explaining that took a whole article and a whole lot of research. So when we started looking at this back in 2015, we didn't really have the basics that we were expecting. So we didn't have a Kleene theorem, we didn't have an axiomatization, we didn't have a decision procedure. And so this had to be fixed if we wanted to extend the framework we had before. And in terms of the axiomatization, to be fair, they did propose an axiomatization in their 2009 paper. They just didn't prove it complete. So it was a bunch of axioms that were obviously sound, but it was not clear you could reason about all the programs using just the axioms. And so these were the axioms of Kleene algebra, plus axioms for parallel that were basically specifying what parallel is supposed to do when it interacts with units and with plus. And then it had this special law called the exchange law that basically talked about the interaction between parallel and sequential composition. And the way to think about the exchange law is very much related to also what I've tried to hand wave in my example, is that you have these two threads in parallel, and they have instructions inside them that they are sequentially composed, and whatever behavior you can see there, it should be more behavior than you would see if you would just look at the parallel of the individual instructions, because there might be things that happen in between that you can capture with that. And so that's kind of what the exchange law is giving you, is basically capturing forms of concurrency that are more than just interleaving. So the interleaving law that says that P parallel Q is PQ plus QP will be basically included in the exchange law. But there will also be other things, other forms of concurrency that will be captured by the exchange law that are much more than interleaving. And so basically this led to Tobias's project CoNeco, which stands for co-induction. Sorry, I'm blanking out now. Co-induction networks and I'm completely blanking out now. Concurrency networks and co-induction. And basically Tobias tried to work through the missing pieces of concurrent Kleene algebra. And that included the Kleene Theorem, which appeared in a paper in 2017. And it included basically the axiomatization and the decision procedure at once that appeared in 2018. And so basically at this stage, we had the basics of the algebraic framework we needed. Let me see what time it is. Okay, let's just very briefly look at the sort of the basics of Kleene Theorem. So the Kleene Theorem ended up using a model that goes back to Gischer in 88, and that's called fork automata. So the way to think about fork automata is you have a bunch of normal automata, normal deterministic automata, and now you compose them together by having forks. And forks basically tell you are doing a parallel, and this parallel is characterized by another automata. Now, what is the catch? The catch is that at the end of the execution of the simple automata, you must join again. So it's kind of you fork and you do something, but at the end of the two threads, which might not be synchronized, so you might have delays, but you still must join the threads. And so that's kind of represented in the automaton. You see I can't point, but you see the branching in state Q1, and then it has a transition with dots. And so that transition basically says you branch into Q3 and Q4, but at the end of whatever you do in that Q3 and Q4, you must come back to Q2 and continue. So this automaton that is depicted there in the slide is basically accepting the language A at the beginning, then there's a fork, and the fork accepts on one branch just B, and on the other branch just CD. And then after the fork, we must come back to Q2 and still accept E. And so there's a way of translating automata to expressions and expressions to automata. And this was what appeared in this 2017 paper. Unfortunately, the automata themselves are actually quite expressive, more than one would like, because once you start having loops and loops into forks, you might end up with things that you don't want to allow. So in particular, if you look at this very innocent looking automaton that has a branch, and then the only thing Q1 does is loop back to Q0. And if you start trying to understand what the automaton is accepting, you will see that it's basically giving you an infinite branching. So it's giving you an infinite parallel of threads. And these are things that you don't want to have. So basically what we have in that paper is also a syntactic restriction on the automata to avoid that such situations arise. Okay, so basically this gives you CKA. And now we would like to look at CKAT, meaning you start with CKA and you add constructs to reason about control flow. And then hopefully, based on CKAT, then we can add the networking operators and the congestion, etc. Now, as I said some while ago, CKAT was actually proposed by Peter Gibson in 2014. And Peter Gibson did the obvious thing, one would say, which was basically to say, okay, these guys took Kleene algebra and added a parallel. Let's not take Kleene algebra, let's take Kleene algebra with tests and add a parallel. I mean, what can go wrong? And indeed, he wrote this very nice paper on the algebraic theory of such system. You basically have two Kleene algebras, one that is a Kleene algebra with test and one that talks about the parallel, and you put them together. And there's, in principle, there's nothing wrong with this, and the paper is sound. So when you read his paper, you have the impression you're kind of done. You have the right basis. So we could now maybe extend Kleene theorems and axiomatizations, etc. But in principle, he has done it. Now, what is the problem? The problem is that if you mash things together in this sort of obvious or naive way, you can end up proving some very interesting things. So in particular, I want to show you one little proof. Imagine you start with this program P, E, not P, where P is a test. Now, P composed with E, we know from the axioms, is smaller or equal than P in parallel with E. So P parallel E has more behavior than just the sequential composition of E. In the similar way, not P, the test not P, is the same as parallel with skip, which is the unit of the parallel, okay? Then in the third step, you use the exchange law that tells you that P parallel E, sequentially composed with not P parallel 1, has less behavior than if I do P composed with not P in parallel with E composed with 1. Now at this stage, E composed with 1, sequentially composed with 1 is E, and we have P composed with not P, which in CKAT, the sequential composition is the same as conjunction. So P sequentially composed with not P is bottom, and therefore, is the 0 of the algebra. And 0 parallel E is 0, because 0 is the abort program. And so suddenly we have proved, what we have derived is that P composed with E, composed with not P is 0. And if you recall the connection with Hoare triples, what we basically have just shown is that every test is an invariant of every program. Now, as algebraic reasoning with no context, this is perfectly sound. As a basis for a verification framework, this is not super useful. So there's something here that went wrong from the verification point of view. And what went wrong is not fully clear at this stage. Maybe it's the exchange law that causes the problem. Maybe parallel with 0 is not 0. Or maybe some of the substitutions we did were, maybe there's some non-congruence going that basically made our derivation unsound. But I mean, according to Gibson's algebraic system, this derivation is fully okay. And now the trick is to note the following, is to make the following analogy. And this appears in a paper by Bergstra and Ponce in 2011. If you have a chicken crossing a road, the chicken might look left, and then the chicken might look right. And while the chicken is looking right, a bike comes. So when the chicken crosses the road, it gets hit by the bike. And so what went wrong with sort of what went wrong with the chicken crossing the road is that in between two sequential actions, looking left and looking right, something in parallel happened. The bike came through. And this is the same thing with tests in concurrent Kleene algebra. In between two sequential tests, something might happen that might make P and Q true. Sorry, P and not P actually might be possible. And so basically what we did was to use that observation. So to use the fact that in the concurrent setting, we cannot anymore identify conjunction and sequential composition. And also you can't identify the top of the tests of the Kleene algebra with tests with the one of the Kleene algebra. And if you do that, you can then basically develop a new algebra of tests, and then you can combine these with CKA in a much, in the same way as Peter Gibson did his CKAT, but now you basically rule out these sort of inconsistencies. And so this appeared actually just recent. So with that in mind, you can then reason about such programs. And you can also show that there are sound and complete axiomatizations and decision procedures, and basically be happy. I hope I gave you a glimpse that, I mean, this sort of combination and figuring out how concurrency interacts with all the components is definitely not, definitely not a trivial project, even though at the beginning we thought everything was there. Many steps had to be taken to actually fill in this diagram that looks perfectly innocent if you put it in a slide like this. And so what Tobias ended up with as a result of his PhD is an algebraic framework to analyze programs with concurrency and control flow. And there's a sound and complete axiomatization and decidability. And we have currently just accepted to concur yesterday a case study using a partial function memory model that can look at the validity of litmus tests. And hopefully soon we will finally tackle what we had in mind 4 years ago, which was concurrent netcat. And so I'm happy to take questions about the technical part, but given the time, before I take questions, I would like to just spend a minute, maybe saying some things more meta, if that's okay with everyone and Valeria. So first I would like to thank the people who worked on this project, and it's mainly Tobias's project, but there's also a bunch of other collaborators, both at UCL and back in the Netherlands. So this, everything I've shown really goes to them, the credit. And then I would like to say a few things about being a woman in logic. And you know, when I was in grad school, I was fortunate enough to be in a great welcoming group at CWI in Amsterdam. And then I did a postdoc in Cornell, which was a fantastic place as well. And I never felt I was a woman in logic or CS or PL, or never. And then I became faculty. And then suddenly the world sort of came crashing. And that's when I realized that actually being a woman in the field meant something, perhaps not as positive as one might have thought. And so I did go through a lot of difficult moments in my career, and a lot of this is not visible to the outside, and a few people know about it, my close friends, but I think it's important that we also share the struggles, in particular in a forum like this. I think it's important that we normalize the fact that as women in the field, we end up suffering things that maybe are not the same for men. So I'll tell you one story. When I started my first faculty job, my very first day, I had lunch with a professor there. And actually one of the organizers of this workshop was visiting, Anna Sokolova. And another colleague came in and asked me, "Are you visiting?" And I said, "Oh, not quite, I'm starting a new job." And he said, "Oh, you're the new hire?" And I said, "Yes." And he walked away. And I didn't know what had just happened there. So I kind of didn't say much and didn't ask much. I thought it was bizarre. After a few days, my office mate asked me to see my CV. And I thought this is a pretty bizarre question from an office mate. And moreover, my CV is on my webpage, but whatever. And then he said, "Do you know the Dutch system is trying to increase the number of women who get hired?" And at that point, and then there were many more incidents for about a month, at which point I talked with my boss at that time, who is still the best boss I've ever had, Herman Hovers. And we had a long discussion about this perception that people had that I was hired because I was a woman. And it took a lot of convincing from him to convince me that I was not hired because I was a woman. And I will never forget, I was very on the verge of quitting at that time. And things went on, and the more ambition I showed or had, the more backlash I got. And that also occurred when I applied to be a professor at UCL. And I got a lot of comments about my age. And this is really, I think, something that no man has ever had to listen to. And I do think, I'm happy to speak offline and to talk to people about such situations and how I handle them. I did handle them with a lot of mentorship and a lot of advice from people. And I would like to stress the importance of mentorship and sponsorship. And these are slightly different things for women. And I, in particular, am a strong advocate for women in the field. And I try to offer a lot of sponsorship, meaning that I put their names through when I have the opportunity, and mentorship when the opportunity arises. And the last thing I'll mention is about PhD supervision. I recently got a comment from a colleague that I'm very motherly. And that comment really, really hit me. I thought, what the heck is he talking about? And then I kind of looked around of my closest collaborators who are men and how they supervise their students. And then I kind of looked at myself and how I supervise my students. And it hit me. I do supervise differently. But guess what? I do think it's a strength. I don't think it's a weakness. And the fact that somehow there's this perception, and I've talked with other female colleagues, and apparently they've had similar comments, that there's this perception that the way women supervise is weaker than men. This should be fought against. And in the current COVID crisis, if you look at the women who are in leadership and the results they had, and the countries that have fantastic, arrogant men as presidents and prime ministers, then I can say that maybe relatable and people who are motherly have actually had more success than people who are not. So if any of you ever hears this as PhD supervisor, I very much, come and talk to me, and I'll share my figures and facts and how this works. And so the last thing, I would like to thank one of the people who have mentored me and sponsored me and also created this workshop. And she has done much more than I think she realizes for me. So a big thank you to Valeria, who has been a great inspiration along the years, but also a great supporter. Okay, and so I end here. Sorry for going a bit over time. And I go back to my question slide in case someone wants to ask questions of any sort. I'm happy to answer, even though we're being streamed to YouTube. I think it's okay.
Many, many thanks, Alexandra. That's been fantastic.